So for this learning module, we'll be computing the moment of a force using a vector-based formulation. This is in contrast with learning module 1 of this chapter, where we did the same thing using a scalar formulation. So if you think back to learning module 1, what really made that challenging, the scalar formulation was fairly intuitive. It allowed us to easily see that the magnitude of the moment, which represented the tendency of that force to induce rotation of the body about that point, could be computed by taking the product of the magnitude of the force along with that perpendicular distance from the point of interest to the line of action of the force. And that just had physical intuition with what we were familiar with. If you remember, I described the idea of opening a door and that being easier when you pushed away from the hinges, or trying to loosen a tight bolt and that being easier when you use a longer wrench. However, that will be a bit of a cumbersome approach when we don't necessarily have all of the geometrical information that we need, or in 3 dimensions when it just is hard to visualize or hard to compute what that perpendicular distance is. So like all engineering workflows, it's going to be easier if we have an automated way to do a problem the same way each time. And for computing moments about points, that is using the vector calculus definition that is described here. Namely, the moment as a vector of the force about a point is given as a cross product of a position vector and that force vector. The position vector is specifically defined as originating at the point of interest about which we're computing the moment and going anywhere to the line of action of the force. So the key point to realize is that your position vector is not unique. And being good at these problems, or at least being efficient at these problems, oftentimes choosing the position vector that results in the least amount of computations. And we will see that in a minute in one of the examples. So as just an example to emphasize the concepts that I just spoke of, here we have a pipe assembly. It has a force that's exerted on it at point B by that cable connected from point B on the pipe assembly to C at some support structure on the wall. And we're asked basically which of these 5 position vectors that are presented could be used to compute the moment of that force about point O. So remember that we can use any position vector as long as it starts at point O and ends along the line of action of the force. And not to beat a dead horse, because we talked about this quite a bit, but when you talk about the tensile force that's exerted by a cable on a support structure like this, its line of action is directed perfectly along the cable itself. So in this particular example, what we're restricted to is choosing position vectors that start at point O and go anywhere along the cable. So since the only 2 designated kind of letter points that we have along that cable are B and C, we can see pretty easily that the only position vectors that will work are ROB, or from the origin to point B, and ROC, from the origin to point C. The examples which initiated A won't work because we're not computing the moment about A, we're computing the moment about O. And I believe they give one that doesn't end, that starts at O but doesn't end along the line of action of the force. Yeah, ROA won't work because point A is not along the line of action of the force. So no, yes, yes, no, no. For the second example problem, we're asked to determine the direction of the moment of the 40 Newton force about point E using component level analysis. I'm going to actually go through and do the math on this one, but I want to show you how, and really this will determine that you're ready to move on from this learning module if you don't even have to make any computations to determine what this answer is. So the reason that we're asked to determine the direction of the moment and not the moment itself is obviously we don't have specific values for the dimensions of this box in order to compute exact values. So we can compute them as a function of those distances, but we don't know those distances. So I'm going to go to a bit of a split screen here in order to get the problem set up. And it helps to have my .cam. Good. So we'll begin, and I'll kind of right over here by expressing the force in rectangular form. So notice as drawn, it acts in the minus C direction, so it will only have a minus k hat component, no I, no j, just minus k hat. And in terms of the position vector, well, what can I choose? Well, it has to start at point E because that's the point about which I'm computing the moment. And I will prove to you in a minute by doing this problem again in a different approach that the easiest position vector to take is the position vector from E to G. Now, how can I express that in terms of rectangular form or in terms of its Cartesian components? Well, I know that it has an x component. It's whatever that distance is, this dimension from point E to point O. So you can just write it as REO. But notice that that position vector goes in the negative x direction. In order to go from point E to any point along the line of action of the 40 Newton force, I need to go back an x. In addition, I'm going to need to go over in y, specifically how far over in y, from the origin to point G. So I'll call that ROG, and these subscript ordering really doesn't matter because they're distances, they're not scalars. So don't say, oh, that should be RGO. It's okay. We all get what we're talking about. And if I choose the position vector from point E to point G, it won't have any displacement in the vertical direction. So that component would be 0. But that is what would change, and we'll keep track of that if we used REB, which also would be valid. So we'll see why we don't do that in a minute. So let's actually compute what this is. So in order to compute the moment, I will take the cross product of the position vector from the point of interest to some point along the line of the action of the force with the force itself. And I'll show you why I'm doing this in a minute, but I'm going to just write this position vector as the sum of two vectors, one purely in the x direction and one purely in the y direction, which I can do for this geometry. And I will take the cross product of that sum instead with the force vector. And the reason that I'm doing this, the point that I'm trying to emphasize, is that the cross product distributes over multiplication. So the cross product at the end of the day is a product. So it's going to have certain properties that are similar to what we know from basic multiplication, right? And this is one of them. It does distribute over addition. However, it doesn't have all the properties of multiplication. For example, we know that it doesn't commute. If you change the order of the two vectors which you're taking a cross product of, the magnitude will be the same, but the sign, the direction, will invert by 180 degrees. So what that tells me is I can rewrite this cross product as two cross products, the x component of the vector crossed with the force plus the y component of the vector crossed with the force. And I can express the x component of the vector using what I have above. I'll write it as REO, and that's just kind of the physical length of that dimensional on the box. That is a minus I hat component. Cross, remember that the force is 40 newtons in magnitude in the minus k hat direction. So that is my first product. And then for my second product, I'll write the y component of that position vector as ROG j hat. And then I'm going to cross that again with the force vector, which has a magnitude of 40 and is in the negative k hat direction. Now, why did I write this a little bit differently in this case than what I usually do? The key thing that I want you to remember is back to the last learning module. I had this diagram, and this is the way that I learned it. So I tend to write it this way. If I ever go back and forth, this is not the way that it's listed on the notes. When you write it in this direction, IJK, this way is positive, and the other way is negative. So that's a little bit confusing to us because we like to think of things that are in the counterclockwise direction as positive, particularly when we're in the moments section. So I intentionally pulled our old notes up. Let me get it here. Too many old notes in order to kind of show you the version of this figure that's in your book. And in this figure, and all that they did, I mean, it's the same definition. I cross J is still positive K in whichever figure you use, but it's reordering the unit vector components such that when you go counterclockwise, it's positive. But just know if particularly if you're ever on a Zoom call with me and I'm kind of just going off the cuff and not prepped, that I might write it on the way on the left. So this is the notes approach. And why do we need this? Well, in order to determine what the direction of this moment is, all that we really need to do is take the cross product of the unit vectors here. So I'm going to go with this one first. The question is, what is minus I hat cross minus k hat? Well, the key thing to know when you're taking these cross products is you can kind of view the minus times minus as just generating a plus, just like standard addition. Don't worry about why that works. You can kind of prove it to yourself geometrically if you want. Just notice that minus I hat cross minus k hat is the same thing as I hat cross k hat. And in order to compute what I hat cross k hat is, if we go to the text here, we'll see that in order to I hat cross k hat, the next unit vector that shows up is j hat. But notice that we're moving not in the counterclockwise positive direction, but in the clockwise negative direction. So I hat cross k hat will be minus j hat. So this is going to be minus j hat, and it will have a magnitude of 40 REO. We weren't asked that though. And then we're going to add on to that. The question next is, what is j hat cross minus k hat? And the key, similar idea here, when you have the plus minus, just hold a minus out and just take j hat cross k hat. And if you notice, going j hat cross k hat is going to give you I hat, and we're moving in the counterclockwise direction, so that's positive. So this result is going to be negative I hat, and the magnitude will be 40 ROG negative I hat. So what this tells you is that this moment has a minus j hat component and a minus I hat component. So the question is, what do these physically mean? Well, remember, minus in moment computations means counterclockwise. Means clockwise. Easy to forget, easy for me to say, even easier for me to spell. And j hat, of course, corresponds to the y-axis, and I hat corresponds to the x-axis. So what this means is that force on that cube would exert clockwise rotation about the x-axis and y-axis. So the question is, how do you see that? Well, if you go back to the slides that we have here, and it's here, the way that you can envision rotation of this box about the x-axis, I'm going to take a book here because it's kind of the same geometry, is imagine holding the book along the x-axis and looking down the positive x-axis and asking yourself, if you exert that force on the book, what will it do? And if you notice, if I'm looking down the x-axis, right, and I'm pinning along the x-axis, that force will rotate in a clockwise direction. So that's what that minus I hat is meaning in this case. It's showing you that 40 Newton force will tend to rotate this book, helps if you can see me, in the clockwise rotation about the x-axis. In order to determine what the rotation would be on the y-axis, pin it along an axis that's parallel to the y, right here, and then ask yourself, look down the y-axis and say, if you push down, which direction would that rotation be? And hopefully you're able to see that that would also be in the clockwise direction. So that's where that minus j hat component is coming from. So just be careful. It's easy, but it's tedious bookkeeping, as you saw with me kind of trying to rush through this and making a little small mistakes that I caught myself on. But if you've had a calc class, again, you might have seen your kind of unit vector cross product circle worded in this way. And that's okay. Just whichever way you do it, as long as you're consistent, it doesn't matter. The last thing I wanted to say is when we worked this problem, we said that we could have equivalently chosen to take a position vector from E to B. And I said that the only thing that would have changed in that formulation is you would have had a component here. And if you had a component here, you would have had an additional term in this cross product that was related to basically k hat cross negative k hat. And if you had an additional term related to k hat cross negative k hat, notice that since k hat and minus k hat are parallel to one another, that the definition of the cross product, which is mag of the two vectors multiplied by each other times the sine of the angle in between, when that becomes 180 degrees in this case, remember that the sine of 180 degrees is going to be 0. So if I were to take a position vector that had a k hat component or a z component, it wouldn't contribute to the resulting moment at all because the cross product of those components would be 0. So hopefully that makes sense. I know it was a little bit quick. I wanted to do a couple of different examples for you. And if you have any questions on this learning module, just email me, or I'm also going to record an additional example where we kind of go through a whole problem formally and get that same physical intuition.